Okay, today's lesson, we are working on a little bit of pre-chapter 6 work as we're starting chapter 6 tomorrow. We're going to review exponent rules and simplifying radicals. You would have done this in Algebra 1, but we're going to need to be good at our exponent rules and simplifying radicals with the unit that we are starting. So we're going to take a day to do a little review. Okay, so we're going to go through all the exponent rules first, and then we'll try a couple examples, and then we'll talk about simplifying radicals. So one of our exponent rules is any number of variable to the power of 0 is always 1. So a to the 0 power will give you 1. If you're not believing me and you want to check on your calculator, 4 to the 0 power is also 1, but we cannot check a to the 0 power in our calculator. So we will need to be familiar with any variable or number to the 0 power is 1. The next rule, when you're multiplying exponents with the same base, you add the exponents. So a and a, those would have the same base. So I'm going to add m plus n as their exponent. In my example, that would be 2 to the 5th power. They have the same base of 2, so I keep that base of 2, and then I add the exponents 3 and 2 together to get 2 to the 5th. A lot of times we wouldn't leave it as 2 to the 5th power, and we'd say this is 32. Make sure you're checking Math Excel. Sometimes they'll ask you to write it as a power, which would mean you're going to put it with an exponent versus just the actual number answer. If you're having trouble remembering what to do with the exponents, you can write this out the long way like you would have done in middle school. 2 to the 3rd means 2 times 2 times 2. And then times, and I'm multiplying by 2 squared, that would be 2 times 2. How many 2's do I have? Well, there would be 5, so 2 to the 5th power. Okay, I have a lot of students that will want to multiply the 2's and they put 4 to the 5th. We cannot multiply those 2's because they are being raised to different exponents. If you follow your order of operations, you'd have to do exponents before you would multiply. Okay. All right, next rule, when we're taking the power of a product, raise each factor to that power. So a times b, that's my product, and I'm raising that whole thing. It's in parentheses to the power of n. So that means a is being raised to the power of n, and b is being raised to the power of n. So in my example, 2x is being cubed, so that means I am cubing the 2, and I am cubing the x. 2 to the 3rd power would be 8, so a better way to write it would be 8x to the 3rd. If you're having trouble like this, or with this rule, you can write it all out. You can take 2x times 2x and times 2x, since that's what I'm raising to the 3rd power, so I'm taking it times itself 3 times. So my 2 times 2 times 2 would give me my 8. My x times x times x would give me the x to the 3rd. Our next rule, when you raise a power to a power, you are going to multiply the exponents. Okay, so this would be considered a power being raised to another power. So then I multiply the m and the n. Same way with my example here, I will get x to the 6th power because I'm multiplying the 3 and the 2. Kind of just like I did that last one. If you wanted to write this out in a longer form, you can take x to the 3rd times itself, because that's what it would mean when I square x to the 3rd. Then from here, you could use the rules of, well, I add the exponents when I'm multiplying powers with the same base. Or then you could resort to going x times x times x gives you x to the 3rd, times another x times x times x to get that x to the 3rd, and together that would be x to the 6th. Okay, so there's multiple ways to come up with this answer. Obviously, just knowing to multiply those is going to be your fastest route, and that's what I hope you understand how to do. But if you're getting these wrong and you're forgetting when you add and when you multiply, string them all out and figure it out. Okay, because the idea is that hopefully it should make sense as to why you would add or why you would multiply. If it doesn't make sense, then you're just memorizing something that you're probably going to forget tomorrow. Okay. All right. Next, we'll talk about negative exponents. We can write them as a positive exponent by taking the reciprocal. So the reciprocal would be to flip this over, and then I have a positive exponent. What happens with negative exponents is it actually is, it's repeated division instead of repeated multiplication. So 4 to the positive third is 4 times 4 times 4. 4 to the negative third would be 1 over 4 to the third. So I am putting 4 times 4 times 4 in my denominator, okay, to get 1 over 64. Okay. All right, next rule, when we are dividing exponents of the same base, we subtract the exponents. Okay, A and A, those are the same bases. So I start with my numerator exponent and I subtract the denominator's exponent. I will always go in that order. Okay, so for my next example, 3 and 3, they have the same base. So I would subtract 6 minus 3. So that's 3 to the third power, or 27. Okay, one thing I'll see students do is they think they can divide this 3 and that 3, but that would be going against our order of operations again, because you'd have to raise the exponent before I could divide. Exponents come before division, so I can't divide the 3's. I could find the value of 3 to the 6th power and the value of 3 to the 3rd power and then divide those numbers to get my 27. That would be possible, okay? But when you notice they have the same base, you can subtract the exponents. Another way you could use, you could figure this out if you're not remembering that you can subtract them. We can go back to writing it all out. 1, 2, 3, 4, 5, 6. So I have 6 3's times themselves for my 3 to the 6th power. And then I have 3 times 3 times 3. Now I don't have any exponent, so it's fair game for me to go ahead and divide this 3 and this 3, this 3 and this 3, this 3 and this 3. What am I left with? Would be 3 to the 3rd. So there are 3 3's in the bottom that get rid of 3 3's on the top. So that's why I can subtract those exponents as my shortcut. Okay. Our last rule here, when I'm taking the power of a quotient, raise each denominator and numerator to that power. Okay, so a quotient would mean division. So a fraction is a quotient or a division problem. So I'm raising my numerator a to the nth power and my denominator b to the nth power. Okay. This problem means to look more like 2/3 to the 4th power. It's just, that's the best way I can make it look when I type it in Microsoft Word. But then I am raising 2, my numerator, to the 4th power, and 3, my denominator, to the 4th power. Okay, 2 to the 4th power would be 16, 3 to the 4th is 81. So I can write that, and always simplify your fractions if you can. There are no common factors. I can divide out of 16 and 81. So that would be my answer. Similar to what I did with up top or some of the other problems, if you're having trouble remembering this, you can write 2/3 times 2/3 times 2/3 and times 2/3 times itself 4 times. So I'm taking the 2 times 2 times 2 times 2 to get my 16, and the 3 times 3 times 3 times 3 to get my 81. Okay, so it's a quick refresher on your exponent rules. Here's 4 examples that we're not just doing one rule at a time. We're going to apply multiple rules to one problem. Okay. My suggestion would be to pause the video, see if you can do these 4 on your own. Then you know you're good to go with the exponent rules. But I'll give you the answers here right now. So I am multiplying. So you really don't need the parentheses necessarily. It's just to kind of separate the 2 things you're multiplying together. So what can I multiply together? I can take 5 times -3 is -15. And I have a common base of a. So then I'll go ahead and add the exponents. So 3 plus -4 would be a -1. And then I'm only going to use positive exponents. So I will not leave that as a negative exponent. Remember, I kind of talked about negative exponents are not a negative number. They mean that you are doing division. Okay, so when we had our exponent rule, we did the reciprocal. So I put 1 over. A. Before we never had a number in front. Right now I have a number in front, so that means I'm taking negative 15 and dividing it to a to the first power. You don't need that first power there. So just negative 15 divided by a would be my answer. Okay, number 2. So I'm taking everything inside those parentheses and I'm raising them to the second power. So you can write negative 4 squared, x to the negative third squared, y to the fifth is being squared. This is a step that you can skip if you're doing this in your head. That's fine. I just want to show you that every separate or every different number and variable is being raised to that power. So negative 4 squared would be a positive 16. X to the negative third, raise that to the second. You are multiplying those exponents. And then I am also multiplying the exponents on y. And then I'm not going to leave a negative exponent. So that's going to need to go to my denominator because I'm going to change it to a positive exponent when I change it to division. It means I'm repeatedly dividing. So then 16 y to the 10th would be left on top because everything there has a positive exponent. X to the 6th goes to the bottom to now be a positive exponent. Number 3, I need to raise everything. This is my exponent of 3. I'm going to raise everything in there to the third power. So 2 is being raised to the third power. X to the 4th is being raised to the third power. I'm raising a power to a power, so I multiply those exponents, and also 3 is being raised to the third power. So make sure you raise every different number and every variable. Okay, 2 to the third would give me 8. X to the 12th will still be x to the 12th. 3 to the third is 27. I can't simplify 8 over 27. That will be my final answer. With number 4, I'm doing a division problem, so we need to simplify this as division. So 12 divided by 4 would give me 3. When I'm dividing with common bases, I can subtract those exponents. So when I have x to the 5th over x to the negative 1st, I take the top exponent and I subtract the bottom exponent. Since my bottom exponent is negative, I will end up subtracting a negative 1, so I get positive 6 for the exponent on x. There's no other y's to either have to add or subtract exponents with, so this will be my final answer. Okay, that is a quick review of exponent rules. You have some problems in Math Excel following the exponent rules, and then we'll have some problems covering, reviewing, simplifying radicals. Okay, so we'll go into this part next. I'm gonna call it a radical symbol when you see a square root symbol, because tomorrow we'll start talking about cube roots, fourth roots, fifth roots, okay, and not just square roots. So we're gonna call it a radical symbol because then a radical represents any type of root. Okay, the term radicand is what's inside of your radical symbol. So B is the radicand. Your radical symbol here would imply a positive or what's called a principal root. We'll talk more about what other types of roots there would be. So your value C would be a square root of a number if C squared would give you the value inside of your radical. When we're simplifying our square roots, we need to look for the greatest perfect square factor. Okay, so here's some examples in this box of some perfect squares. So whenever I take a number to the second power, it is a perfect square. So 1 squared is 1. We never really use 1 as a perfect square because it doesn't change anything. But 2 squared, 4 is your perfect square. The square root of 4 would be 2. Okay, and so on. So all of these bold numbers right here, those are all of my perfect squares. Okay, there's more. Obviously, I can do 16 squared, 17 squared, and keep going and going. But it gives you an idea. Those are the ones that we are working with. So if I look at this example 1 that's been worked out for me, and I have reviewed this a little bit really quickly when we did the quadratic formula and some of our complex numbers, we had to simplify some radicals. So 50, 25 is a factor. 25 divides into 50 2 times. So that means it's a perfect square. So then I can separate it into the square root of 25 times the square root of 2. Still the same value, that's the square root of 50. But 25 is a perfect square because 5 to the second power gives you 25. So I can take the square root of 5 squared, or I'm taking the square root of 25, depending on the way you look at it. And then the 5 comes out, and the square root of 2 would stay in because I cannot take the square root of 2. There are no other. 4 doesn't divide it, and 1 we never use. So that would be my final answer. The second example that's worked out for you would be the square root of 300. So 300, larger number. The largest perfect square factor would be 100. Now things like 25 and 4 do go into 300. But if I take 25 into 300, so for example, because this may happen to you. So if I do 25, 12, so 25 times 12 gives me 300, but 4 is a perfect square that still divides 12. So then you have to simplify the square root of 12 into the square root of 3 times the square root of 4. So then you have to keep going. Okay, so that might happen to you. So always check if the number you're multiplying by still has a perfect square that could divide it. Okay, because it will take you longer to simplify. Okay, but if we use 100, 100 is a perfect square because 10 squared is 100. What is the square root of 100 is 10, so that number comes out. 3 is what's remaining. There are no perfect squares that divide 3, so I'm done. It's possible some of you learn to do this. I'm seeing more of this now with factor trees. So maybe you did like 5 times 10, 2 times 5. Oh, look, 5 times 5 was written twice, so then I put 5 and I leave 2 in the square root. I've been seeing kids do more of that when they do these problems. So if that's the way you learn, that's fine. Not typically the way I teach it or the way I learned it. So I talk about just perfect squares, but not wrong. If that's the route you're going, go for it, if that works for you. Okay. Some other little radical rules that we'll continue to talk about as we jump into our chapter 6. So we can write things as 2 separate radicals if they are a product. So kind of the same way as I have the square root of 300 is the same thing as the square root of 100 times the square root of 3. Okay, same way if I have a fraction, I can separate the numerator to just a square root and the denominator as just a square root. Okay, if I'm taking a square root times itself, I'm just going to get that result. Okay, and then the square root of anything squared is going to be the result that you had inside. Or just that x, if you had x squared. If you had 5 squared, you get 5. If you had square root of 3 squared, you get 3. Okay, all right, so then I have a few examples below for you to try out. So if you want to pause the video now and test yourself to see if you understand the radical rules, you can do that. But with the first one, I can't divide 25 and 81 without getting a decimal. I don't want any decimals in my radicals or in any of my answers. Okay, so I'm going to need to take the square root of 25 on top and take the square root of 81 on the bottom. So on top I get 5, on the bottom I get 9. That would be my final answer. Okay, with example 4, I can't take the square root of 24 itself. I cannot take the square root of 6 itself. So here, it's actually better if I think of it and I change it into a single radical, kind of the reverse of what we did. With example 3, I had everything in one radical and then I separated it to take the square root of the top and bottom. This one I had them separated, but now I put it as one big one because what is 24 divided by 6? Well, that's 4. So then I can take the square root of 4 and get 2. Okay, not all of them are going to turn out nice. if I look at example 6, which should be a 5 if we go in numerical order, the square root of 7 is not nice. The square root of 3 is not nice. If I rewrite it as 7 over 3, I still can't divide them. So it doesn't make it any easier to do that either. Okay, so you're kind of stuck on one like this. This is going to be what's called rationalizing the denominator. You did this probably in geometry and in algebra 1. You can't leave a radical in the bottom if we weren't able to, like take the square root in this one or divide them so there wasn't a denominator. Okay, then I have to multiply by the square root of 3. Because if I take the square root of 3 times the square root of 3, I would just get 3. So then I would not have a radical in the bottom, so then I also do that to the top. So I'm multiplying the square root of 7 times the square root of 3, would give me the square root of 21. In the bottom, when I take the square root of 3 times the square root of 3, I get 9, which is 3. And then I can't simplify the square root of 21. There are no perfect squares that would divide 21. So then that would be my answer. Okay, 2 more examples here. So we'll switch this up, 6 and 7. All right, so square root of 20 times the square root of 5. My suggestion is to multiply those together first and then simplify it. Yes, you can simplify the square root of 20 into the square root of 4 times the square root of 5. Some students kind of create more of a mess when they do that. I usually tell them to multiply it to 1 and then see what you can simplify from there. So I'm simplifying one radical versus simplifying the square root of 20, then multiplying it together to simplify again. Okay, so the square root of 100 would give me 10. The last one here, example 7. So I'm going to multiply those together. I can't simplify the square root of 6 or the square root of 3 as they are. The 4 and the 2 are both on the outside of the radical, so those can multiply together to give me 8. And then I have the square root of 6 and the square root of 3, because really this is 4 times the square root of 6 times 2 times the square root of 3. So students have a hard time kind of detaching those from their radicals, but if everything's multiplication, you can multiply in any order. So I can rewrite that as 4 times 2 times the square root of 6 times the square root of 3. And it's still the same thing as what I was doing. Okay, I can't do that if I'm adding. Okay, so then 4 times 2 is my 8. The square root of 6 times the square root of 3 would be the square root of 18. And then I need to double check. I've got 18 in my square root. Is there a perfect square that could divide 18? Yes, 9 times 2. I use 9 because the square root of 9 is a perfect square. That gives me 3. I'll leave the 2. I still have that 8. So then 8 times 3 would give me 24 square roots of 2. Okay. All right, so it's a quick radical review. Go ahead and try your homework in Math Excel. And please let me know if you have more questions on this. Some of you that might have been all the review you needed and you remember it from your previous courses. Others of you, both of these topics maybe were really challenging and you didn't do well on them when you first learned them. Okay, so please let me know if you need help. All right, bye.